Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 26, Organic Chemistry 2. Today we will continue on chapter 5, Enols, Enolates, and the Aldol condensation. We will talk about attack by enolates on the carbonyl reaction, we call it Aldol condensation. We will talk about cross-aldol condensation and intramolecular aldol condensation. The aldol condensation is a condensation reaction in which an enol or an enolate ion reacts with a carbonyl compounds to form a beta hydroxyaldehyde or beta hydroxyketones, followed by dehydration to give a conjugated enon, what we call it alpha beta unsaturated carbonyl compounds. We can perform this reaction under base-catalyzed condition, so the base removes proton from the carbonyl, alpha carbonyl, the alpha proton here, okay, to form enolates. The enolate attacks the carbonyl carbon electrophilic center, followed by protonation to give a beta hydroxy carbonyl. Removal of another alpha hydrogens to form enolate again, followed by loss of hydroxide in a strongly exothermic step to give final product alpha beta unsaturated carbonyl. In an acid catalyzed condition, protonation takes place on the oxygen, followed by deprotonation of the alpha hydrogen to form enol. The enol will attack on the carbonyl carbon, the electrophilic center here, to form beta hydroxy carbonyl, followed by dehydration to form the final product alpha beta unsaturated carbonyl. Reaction of butanol with 15% potassium hydroxide in water provide the beta hydroxy aldehyde. The first step, as we mentioned again, we say it again, deprotonation of the alpha hydrogen, forming the enolate, which stabilized by resonance, of course. Then attack of enolate on another molecule of butanol, the partially positive center here, to form this anion, which gets proton from water to give the beta hydroxy carbonyl compound. In 1 molar sodium hydroxide and elevate the temperature to 80-90 degrees Celsius, we get the alpha beta unsaturated aldehyde. The mechanism is the same: deprotonation, forming enolate, nucleophilic attack of the enolate to the carbonyl carbon to form this anion, protonation to give beta hydroxycarbonyl. Another molecule of the base will attack on the alpha hydrogen again to form enolate. This enolate will lose OH to form the final product. The loss of water here proceeds via what we call it unimolecular elimination, unimolecular conjugate base. So that the first step actually forming conjugate base from that acid, then it loses the OH to form the final product. The elimination unimolecular conjugate base mechanism is different from E1 and E2 mechanism. In E1, recall, it's two steps. First step is leaving group, breaking the carbon leaving group, forming the carbocation, then elimination of proton, breaking carbon hydrogen bond. In E2, it is one step. So while CH breaking, Cl breaking, and C double bond is forming. In E1CB, it's two steps. But the first one is a CH breaking, forming carbonyl, then breaking the carbon leaving group and the formation of C double bond C. If we have acetone treated with DOX50 H plus resin, it gives the alpha beta unsaturated ketone. The first step is enolization using acid as a catalyst to form enol, which attacks on the carbonyl carbon, forming this species, minus H plus H to give that structure, beta hydroxycarbonyl, which again protonated on this oxygen, followed by elimination of water to form a carbocation, then loss of proton to furnish the alpha beta unsaturated carbonyl. Reacting cyclohexanone with HCl give this beta chlorocarbonyl compound. Here is alpha, here is beta. Can you explain its formation? Cyclohexanone in acidic medium, some molecules will get enolate. Then the enol form will attack another carbonyl of cyclohexanone to form this species, minus H plus H give this one, protonation on the OH oxygen will get this oxygen plus species, loss of water will give this carbocation, Cl minus attacks on the carbocation center to furnish the product. Predict the products of aldol condensation followed by dehydration of the following aldehyde and ketone: butyraldehyde, A and B acetophenone. Let's start with butyraldehyde. This is the alpha position. Okay, here another species. The first step will be enolization and formation of double bond between these two carbon, then attacks on the carbonyl to get beta hydroxycarbonyl, followed by dehydration. So this is the expected product. Here is acetophenone. Here is the alpha position. This is the carbonyl, another molecule. Attack, enolization first, followed by attack for beta hydroxy, elimination of water to get this is a product. Remember that we are expecting to have E and Z mixture. When the enolate of one aldehyde or ketone adds to the carbonyl group of a different aldehyde or ketone, the result is called Crossaldol condensation. The compounds used in the reaction must be selected carefully, or a mixture of several products will be formed. I have an example here: reaction of ethanol and propanol in base could lead to 4 different products. We have either the ethanol gets enolated and then attack another molecule of propanol or from ethanol, or the propanol gets deprotonated and attacks another molecule of propanol or ethanol. So we have 4 different possibilities and 4 different products. Predict the major products of the following base-catalyzed aldol condensations with dehydration. A. Benzophenone plus propionaldehyde. B. 2,2-dimethylpropanol and acetophenone. Let's look for A here. Benzophenone, carbonyl with no alpha hydrogen. Propionaldehyde, yeah, there is alpha hydrogen here, so in presence of base we will form the enolate of the propionaldehyde, followed by attack on the carbonyl carbon of benzophenone to give this beta hydroxy carbonyl, followed by dehydration to give this final product. For this compound, we have here no alpha hydrogens. For the acetophenone, there is alpha hydrogen. So what we expect here, formation of enolate on this carbon, followed by attack on the carbonyl, forming this beta hydroxy carbonyl compound, dehydration to furnish the final product. That's what we expect. Cinnamaldehyde is used as a flavoring agent in cinnamon candies. Show how cinnamaldehyde is synthesized by a cross-aldol condensation followed by dehydration. This is the structure of cinnamaldehyde. We have here alpha, beta, double bond. We can get this from beta hydroxy carbonyl, and alpha beta cleavage of this bond will give the starting material. It's benzaldehyde and acetaldehyde. Indeed, reacting this together in presence of potassium hydroxide will furnish the beta hydroxy compound followed by dehydration to give cinnamaldehyde. Intramolecular aldol reactions of diketones are often useful for making a 5 and 6 membered rings. Aldol cyclization of ring larger than 6 and smaller than 5 are less common because larger and smaller rings are less favored by their energy and entropy. Here we have hexane dial. We have here alpha site of enolate, enolization of this center attacks on the other carbonyl to form this beta hydroxy carbonyl, followed by dehydration to form the cycloalkene carbaldehyde. If we have hexane 2,5 dione, we can either have this center carbon as enolate or that one. For that one, we will form 3-membered ring, unfavored strain ring formation. So it would go back to this carbonyl enolate, which forms the 5-membered ring followed by dehydration to give 3-methyl cyclobent 2-ene 1-on as a product. Show how octane 2,7 dione might cyclize to a cycloheptanone. Explain why ring closure to cycloheptanone is not favored. For the octane 2,7 dione, we have 2-alpha center. If this carbon gets deprotonated to form carbon neg-, which then attacks on this carbonyl carbon, 7-member ring will be formed. On the other hand, this one, if gets carbon minus, attacks on this carbon again, that will be 5-member ring, which is more stable. The formation of 7-member ring is unfavored for entropy reason. The further apart the nucleophile and the electrophile, the harder time they will have finding each other. For entropy reason, this will not be formed, and this will be the major final product. See you next lecture.